Welcome to Pre-Tower with K&M Technology Group. Here we will have discussions and presentations with technical specialists about topics or problems that are affecting the drilling industry today. We strive to keep the discussion strictly technical, with no sales pitches for products or services. But since we are conducting a technical discussion, for context you should know who we are and what we do. K&M is an engineering consulting firm that specializes in complex and challenging wells. We began with a focus on extended reach wells and have evolved into a company that handles any type of challenging wells, be it unconventional, HPHT, deep water, deep TVD wells, and more. Our highly trained team provides engineering consulting, training and best practices, and field supervision. We also developed ERA, our proprietary torque, drag, hydraulics, and geomechanics software, which makes well planning more accurate and efficient. To learn more, please visit our website at www.kmtechnology.com.
Welcome, welcome, welcome. Thank you again for everybody for joining us on this now our eighth or ninth, I think. Pre-Tower with K&M Technology Group. My name is Chris Cutts. I'm the general manager with K&M Technology Group, based here in Houston, Texas. And with me today, I've got the esteemed Jason Kroger. Jason, introduce himself.
Morning, everyone. I'm Jason Kroger with K&M. I'm the operations supervisor, and I'll be helping out Chris today. There I am.
Okay, now some technical difficulties. Now there's Jason.
Good morning, everyone.
So before we get started today, I just wanted to mention that, this is our 8th episode that we've done. We have a lot of fun doing it, and we're going to continue to do it for quite some time. For those that are watching regularly, we have we've not only had K&M people on this webcast. We've had a number of people from industry that have come in to talk about technical topics that are related to the drilling world. So we've had somebody from scientific drilling come in to discuss magnetic ranging, and we've had experts come in to discuss wellbore positioning and surveying and tortuosity. So if there's anybody else out there who has a technical topic that they would like to discuss, if there's any companies out there that have had a very interesting success story that they would like to discuss, or maybe a lessons learned on something that had happened that they learned a lot about, if there was a specific instance that was an MPT event or a situation that was unique, that an in-depth investigation was done and something new and interesting was determined based off of the results of that event, we'd love to hear from you. So if you're interested, then by all means go to our website. We just had it up there on the screen recently, www.kmtechnology.com. Send us a link. Send us something to say that you'd like to be on the show to discuss, and we'll be happy to reach out to discuss if that's something that we would like to pursue. But without further ado, let's go ahead and jump into today's topic. So today we want to discuss some of the challenges associated with shallow ERD wells. We've talked a lot recently about the more typical U.S. land type horizontal wells, and we haven't discussed nearly as much on some of the classic ERD wells and what some of the major challenges are associated with drilling these types of wells compared to some of the more common wells that are drilled around the world today. So some of the biggest things that we run into on shallow TVD wells, one of the biggest concerns is related to ECD. And I don't want to insult anybody's intelligence, but ECD is equivalent circulating density. So when you have your drilling fluid in the well, it's going to exert a certain amount of pressure downhole based on the density of the fluid and the true vertical depth of that fluid is exerting. However, when you turn on your pumps, the annular pressure loss that you have as the fluid is traveling from the bit all the way back up to surface is going to be exerting an additional amount of pressure that can be calculated, that when you take that pressure and divide it by your gravitational constant, and your TVD is going to result in an additional mud weight, if you will, and we call that ECD, equivalent circulating density. I prefer the term effective circulating density because it's effectively increasing the density of your fluid when you turn the pumps on. But this becomes a real concern because the amount of pressure that's required to move the fluid in the annulus based on the drilling fluid, the mud weight, the rheology, the annular clearance, so the size of hole you have, the size drill pipe, that annular pressure loss is relatively fixed for a given geometry. But as you go to shallower and shallower TVD, then the impact that it has is quite significant as you go to shallow and shallow TVD. The other big issue that we run into is from the torque and drag side. And today we want to talk a lot more about axial drag because whenever you drill a well, you have to run drill pipe into the hole to drill the well. You have to apply weight to the bit. That's becoming less and less of a concern with rotary steerable tools, but still in cases where people drill with motors, you still have to apply weight to the bit. And axial drag can become a concern. But then running casing is really where the rubber hits the road on a lot of these wells. The casing that we run is typically bigger, sometimes heavier than the drill pipe that we're running in the hole. And in that case, that axial drag can become quite significant, and some different tricks or some outside-the-box thinking can be required in order to make sure we get the pipe down. And lastly, some of the topics that maybe aren't always on the top of everybody's agenda to think about, but when running liners or going to run a whipstock in some of these types of wells becomes a real challenge because you can be quite limited on what some of the requirements are in order to actually set those hangers, set the packers, or the whipstocks. So let's consider two well paths. So we've got the first well path that's from an Alaska well, the green well path, and then we've got a blue well, which is a more common U.S. land type well. Now, for the sake of this exercise and what we're going through here, both of these wells are approximately 21,000 foot measured depth, and both have about a 10,000 foot lateral section. All the plots that we're going to show assume that the pipe has that these wells are drilled with the same mud weight, same mud properties, and same drill string and same hole size. So we're trying to keep as many things comparable so that when we show what the results are, it's as close to an apples and apples comparison as possible. So because both of these wells have similar well designs and well characteristics, the annular pressure loss that we get at TD for both of these wells is going to be actually quite similar. They're very close. They're within a few psi of each other, assuming that we're pumping at the same flow rate. But we want to go through and we want to look at how each of these well paths are going to impact both ECD. So while you're drilling the well, what is the bottom hole pressure going to look like while you're drilling the well? But what is it also going to look like when you go to pull out of the hole? Because we do see on a number of occasions where you can drill the well real nice, then you go to pull out of the hole, and then either for a bit trip or a tool failure, or even when you get to TD and you pull out of the hole to go to run casing, then you go back to run into the hole, and the hole is destroyed. So what's the reason for that? Why is that happening? So let's jump into ECD. So what we're looking at here first, this plot is showing the measure depth for the well on the y-axis in feet, and the ECD felt at the bit in pounds per gallon on the x-axis. And right now we're going from 8 to 13 pounds per gallon. The green line here is our surface mud weight. So on this particular well, in these wells, we're running 9.3 pounds per gallon mud. The ESD, the equivalent static density, is what is being felt downhole, including, and that typically includes the cuttings that we've accumulated inside the well bore through the drilling process, and those cuttings suspended in the low angle section of the hole are going to add to the density of the fluid. So the ECD is going to be slightly higher. The other color lines that we have here, this gray line over here, this is our minimum horizontal stress, or our fracture gradient. This is the pressure at which, if we exceed that pressure, then we're going to start to open up any existing fractures in the well. So we typically look at this as our upper limit because we don't know if there are any existing fractures in the well or not. And if we stay below that limit, then we reduce the risk of encountering lost circulation or wellbore breathing or ballooning. On the other side, we've got this green, yellow, and red curve. These are all our collapse gradient curves. So those are the pressures that we need to maintain in the wellbore to keep the shales from starting to get crushed under their own weight. And we've got different levels of instability. The green is a low level of instability, the yellow is a moderate, and red is quite severe, or orange is quite severe. There are some wells where you can handle some moderate instability, some minor, maybe even some moderate instability, but typically if you get to the orange area, the well is going to be damaged pretty significantly. And no matter what the mud company says, there's nothing that you can pump into the well that will correct wellbore instability. Once it happens, it's there. You can't fix it. And this very dark colored curve over here, this is the pore pressure. So this is the pore pressure within the rock itself. This green line here is the ECD that the ERD well would feel while drilling the 8.5-inch production hole section at each depth within the well. So we're assuming that in this well we've got the 9 5/8 casing points at a similar depth. We're using 5-inch drill pipe. We're using the same mud properties, mud weight and rheology, and we're pumping at the same flow rate, 500 gallons a minute. When we do the analysis, both of these wells have approximately 475 psi of annular pressure loss at TD. And if we look at the equation for ECD, ECD is annular pressure loss divided by our gravitational constant divided by our TVD plus our current mud weight, or ESD. So at TD, this particular well, if we have 9.3 pound per gallon mud at surface, remember that's what is going to be reading on the mud engineer's report. Then we're going to have about 11.7 pound per gallon ECD when we get to TD. For the U.S. land well, with similar everything, we're just now making the well path deeper. Same horizontal length, everything is just deeper. Now, because that same 475 psi pressure of annular pressure loss is being felt at a much deeper TVD, our ECD is significantly lower. So now we're at about 10.4 pounds per gallon. So we see a significant reduction in our drilling ECD, drilling to similar depth, similar measured depth, with everything else being the same, with a deeper well compared to a shallower well. So that's about a 1.25 pound per gallon equivalent increase. That would almost be the same as the mud engineer every time you turn off the pumps, jacking up your mud weight by 1.25 pound per gallon. That's the hole doesn't feel it any different. The hole feels that same amount of pressure. That's essentially what the hole is going to feel. And there are probably a lot of areas that people drill in where an extra 1.5 or 1.25 pound per gallon might make it extremely difficult to continue to drill the well. So it does make a big difference. But drilling is one thing. Now let's look at pulling out of the hole. So if we look at swab, so the swab effect is going to occur when you're pulling the pipe out of the hole. Swab is normally most people think about swab or swabbing as a well control issue. Swab is not only a well control issue, it's also something that has to be taken into account when we're drilling through high angle well bores. Primarily because as you pull the pipe out of the hole, there is going to be a reduction in bottom hole pressure. That reduction in bottom hole pressure can be significant enough where you can reduce the pressure downhole below one of those thresholds that we looked at. So here we're looking at a similar plot where we've got measure depth on the y-axis and ECD felt at TD on the x-axis. So in this case, imagine that we put a gauge down at TD at the very end of the well, and this is this green curve is what would be felt at TD if we pulled the drill pipe and the BHA out of the hole at 100 foot per minute as we got all the way out of the hole. So the same factors that impact ECD also impact swab. So your annular clearance, your drilling rate, drilling fluid, primarily the rheology, density, of course, and instead of pump rate right now, we're looking at tripping speed. So on this particular well, we would see that with a 9.3 pound per gallon equivalent mud weight, if we tripped out of the hole at 100 foot per minute, effectively, if we had a pressure gauge downhole at the toe, it would read 9.2 pound per gallon at the toe. And as we trip more and more pipe out of the hole, as we have less pipe in the hole, then the swab load will become less. But according to this model, this would indicate that we would have to trip out to about 6,000 feet before the bottom hole pressure at the toe would be above the highest threshold for the wellbore collapse. So over this entire span, we would have not only been below the collapse gradient and the well would have been falling apart on us, but the one interesting thing about this particular well, this well in Alaska, these reservoirs are conventional. They're not an unconventional reservoir where it has little to no permeability. These wells have very good permeability. So by tripping out of the hole and going below this line here, the pore pressure, we could actually be not only collapsing the wellbore, but inducing a kick. And trying to circulate out a kick in a wellbore that's been collapsed would be an incredibly challenging and difficult situation to try to accomplish. So the swab effect is one of the biggest things that need to be taken into account for constructing high angle wells. Conversely, if we look at the U.S. land well path, so now because we're at much deeper TVD, that swab effect is much less pronounced. So in this case, we would not be going below pore pressure, but we would still be below that point where the well will be starting to fall apart. And in this case, if you tripped out of the hole and your bottom hole pressure goes below the pore pressure and you see an influx, then you're going to see that at surface. At least you should see that at surface. You should see the hole taking improper fill, and you should see you should see something that's going to indicate that you've taken an influx. If you go below the collapse gradient, then there's no feedback at surface to indicate that the well is starting to fall apart. And the only time you find that out is after you've pulled out of the hole, and then you go back in with your next drilling assembly or your clean out assembly or your casing, and then you start to have a hell of a time getting your casing down to bottom because now the hole has started to fall.
So Chris, I love this plot. This is a very common misunderstood concept that I've run across a lot. And so this is a gauge plot. So this is what your hole fills at TD. There are several sections of your lateral that are going to be different for your collapse gradient. Not so much on pore pressure, maybe a little bit if you've crossed over some different formations. But how do we solve this problem? What's the solution to get at this? You know, if I should know this before I even drill this well, then I'm going to have to either back ream out of the hole, pump out of the hole. What are my possible solutions here?
Well, you've got a couple solutions here. So you can, the one way to overcome the swab effect is to turn the pumps on. So if you turn the pumps on, then you're overcoming that swab effect. Now, some people like to do the pump just enough fluid to displace the volume of steel that you're displacing, kind of just tickle the pumps at a few strokes per minute. That may help overcome the swab effect, but that also has a pretty big impact on barite sag. So if anybody's ever experienced barite sag, if you just introduce just a little bit of shear into the mud, it kind of induces that perfect storm for barite to start to sag out. And then you start to see, if you're running 9.3 mud, you're going to see 8.2 and then 9.9 and 10.1, and it's going to be all over the place.
Yeah, and if you're close to your pore pressure and you're getting the barite sag, suddenly you're dealing with a kick. You're starting to have well flow. So that may not be the best option. It may be a high flow situation. If you've got high flow and you're trying to pull out, what are the problems that are going to come up with that? You just drilled a well, and you're going to say, we don't want to induce barite sag. We don't want to rotate the pipe. We just want to pump at a high rate. What are the risks associated with that?
Well, everybody's heard horror stories about back reaming, about how back reaming causes so many bad events, and you should never back ream unless you absolutely have to. I agree to a certain extent, but back reaming can still be a very powerful tool, not only for effectively cleaning the hole, but also to help overcome swab. So you either have the choice of pumping out with full parameters or back reaming out with full parameters. I think it's been proven by many operators around the world that rotation in high angle holes is really the key to effectively cleaning the hole. And when we go to back ream out, or when we go to pump out in a high angle hole, the flow around the BHA is likely going to be turbulent flow. There's going to be a lot of energy, and it's going to be stirring up any little cuttings that are going to be there. So over the length of the lateral, and we're talking a 10,000-foot lateral here, you're going to be stirring up a lot of those cuttings. And if you don't have rotation, they're just going to get deposited directly on top of the BHA. And at some point, that dune can become large enough where you're just going to pull the BHA into it. And what's very common is an operator will say, well, I circulated my 4, 5, 6, 7, 8, whatever number of bottoms up at the recommended flow rate, recommended parameters. And so the hole should be clean. So if at that point they're pumping out and they pull into something, they start to see overpull, very rarely is that thought to be cuttings because they've already blessed the hole to say that it's clean. And why would anybody trip out of a dirty hole? Then it results in overpull, and if you pull into it, you turn on your pumps, then the cuttings that have built up around the BHA at that point are going to act as a plug, and then as the pressure from your fluid goes out the bit, encounters that, it has nowhere else to go, causes a pressure surge that everything down below that point is now exposed to, and then you can damage the rest of the wellbore. So you can actually, they call it a hydraulic hammer effect, where you can actually cause the rest of the wellbore from that pack-off point down below to be completely damaged, where you might actually lose that portion of the well. The other aspect of it is back reaming, which back reaming it would be considered a high-risk operation. But provided that it's done safely, back reaming is done on operations all over the world successfully. The real trick to back reaming is you have to be patient, because you don't really see a lot of cuttings at surface when you're back reaming. You typically only see them as you get closer to surface. This is also really important for cased hole, because if you've got high angle cased hole, swab still happens in cased hole. I've heard it, I don't know how many times, that people say, I'll be really careful when they're tripping in the open hole, and then what do they do when they get inside casing?
Rip it out.
They just pull as fast as they can.
Fast as you possibly can, that's right.
And then at that point, there's if the hole is clean and the casing is clean and you get inside casing and you start yarding the pipe out of the hole, you're not going to see any indication that the hole is falling apart.
Yeah.
And then you go back in with your next assembly and it's a complete mess. So we've seen numerous times where it is a requirement to continue to back ream inside high angle cased hole, because the cuttings don't care whether they're an open hole or cased hole. If it's at high inclination, they need to be moved out of the hole the same way. You could actually argue that cased hole is could be even riskier than open hole, because cased hole is got to be gauge. There's always a possibility that the hole could be slightly over gauge when you're inside open.
So we're talking about putting an entire BHA, rotary steerable, all that is inside a cased hole, turning 150 RPMs, cleaning the hole. That's actually a very foreign concept for a lot of people, but we've executed it. What do you say? Hundreds of times.
It's been done numerous times, and the majority of wells in Alaska do it on a regular basis, as well as other places around the world. It's a very common concept for extended reach projects where they have to back ream inside cased hole with full parameters. Another thing about ECD that is a common misconception that impacts a lot of ERD wells is how it varies throughout the lateral. So it's a very common thing where operators will go, and after, like when they go to drill out the shoe, they'll do their FIT test. And when they go to do their FIT, if at some point you get let's say you place the shoe in a shale that's maybe a little bit more fractured than normal, then you can have your actual leak off be significantly lower than what your expected leak off is, or even just your FIT. If you're just planning on doing an FIT, just pressuring up to a certain amount to say, okay, we know that the shoe can handle X amount, but you don't actually see fluid get pushed into the formation. But then partway through, you actually start to see that you're losing fluid. Well, now you know that there are fractures at that point that can only handle a certain amount. The issue then becomes, how do you manage that? Because at that point, especially if it's a high angle hole, at that point, the ECD will be somewhat consistent, provided that the flow rate and rheology and everything else stays consistent. But as you drill further and further out, ECD has to increase. There's no way around it. It has to increase as you drill further out. So we can actually model the ECD to say, what do we need to do to permit keeping the ECD below that actual leak-off result, but allow us to drill the TD to stay within whatever other limits that we have geologically within the system that can allow us to actually drill the well to TD. And that can all be done with model. So with regards to, so here we're looking at an ECD sensitivity plot. So on the y-axis, we're looking at measured depth in feet, and on the x-axis, we're looking at pound per gallon and ECD in pound per gallon. So again, the green line is our surface mud weight, and the pink line is our ESD. So if we're looking at the ECD at the 9 5/8 casing shoe, right now we're sitting, depending on our flow rate sensitivity. So here we're doing a flow rate sensitivity. We're saying our base case rheology parameters for 600, 300, 200, 100, 6, and 3 are shown right here at 5, 32, 25, 18, 6, and 5 respectively. And then what we look at in the sensitivity rheology is we've got 80%, 90%, 100%, 100, 120. So what that means is if we assume that all of those rheology parameters go down by 10% or 20%, then we recalculate the ECD at every depth, assuming that this is the mud was 20% thinner, if the mud was 10% thinner, if the mud was acting exactly as we've listed in our spec sheet, and this is if the mud became 10% thicker, and this is if it became 20%.
So why are you showing rheology for an 8.5-inch hole? Why not flow rate?
Because when you get into smaller hole scenarios, like 8.5-inch hole or anything smaller, typically rheology has the biggest impact on your ECD. Modifying flow rate can have as much of an impact, but we typically see that as the mud starts to get thicker, you're going to see the biggest variation in your ECD. Mm-hmm. And most of the time, when you're going to be drilling your production hole section, you've already decided what your flow rate is going to be already. Not to say that you can't look at it, it still should be looked at. But the most common sensitivity that we look at in high angle production hole sections is going to be the rheology.
And so at the bottom of the graph, you've got it circled there, and there's a kick out on the ECD. Why is the ECD a little bit higher right there?
So the ECD is going to be a little bit higher right there, and that's primarily going to be around the BHA. Because around the BHA, we're going to have much larger components, where we're going to see a marginal increase in the amount of annular friction pressure around those components. So that's why we're going to see that kind of kick out.
So that kind of explains like sometimes where we have a little bit of seepage losses when we drill into a new zone. And then when we drill past it with the BHA and the drill pipes over it, your ECDs fall off, your losses go away. Is that right? That kind of explains the phenomenon?
That could be one reason for it. Yeah. The other reason for it is when you drill through a new zone, if the zone is completely exposed, you're going to if you haven't been able to build up any filter cake yet, you're going to be losing some fluid in there while that filter cake gets built up. Once the filter cake is built up, then your fluid loss through that zone would tend to go down.
Gotcha.
But as we continue to drill in this whole section, as we get to TD, our ECD is going to be somewhere between 11.4 and 12 pound per gallon. But that's not going to change the ECD back to the 9 5/8 shoe. Provided that all of these parameters stay the same, that we still flow at the same flow rate, that we keep our rheology within the same realm, then the ECD at the shoe shouldn't change, and we still should be able to drill the TD while staying below that threshold. We just don't want to get to a point where if you have a failed FIT, that you assume that failed FIT applies for the entire whole section. There could have been something that happened during the cement job or while immediately drilling out that resulted in that FIT being or that leak off test being below whatever your FIT was. You want to make real time decisions based on what you actually see.
Yeah, and this is our snapshot plot, which at each depth, this is what each section of the hole is filling. So 9,000, it's filling just below 11, et cetera, all the way down to TD. So it's a graduated, scaled ECD. The hole fills.
Correct. And it kind of brings up the issue again that ECD is not typically something that can be corrected at the well site. The guys at the rig, they have limited control over what they can actually do to mitigate an ECD problem. They don't have any control over how long the well is. They don't have any control over the hole size. They don't have any control over the drill pipe size. They can manipulate the flow rate a little bit, and they can try to make the mud a bit thinner if possible, but they're pretty restricted in what they can actually do to mitigate an ECD problem.
Mm.
This is really an engineering solution. The best way to solve an ECD problem is the engineer has to take control over it. And then that kind of gets into, because we get asked a lot, well, if I have an ECD problem, I'm just going to throw MPD at the situation. The issue that we see with MPD, and I like MPD. I think it's great technology. I think there's a lot of wells that absolutely require MPD to be successfully drilled. But I do see very often that MPD is used as either a crutch or a means of not putting in the appropriate amount of drilling engineering effort required to successfully plan the well. The thing about MPD is, what's commonly said about MPD is that it has constant bottom hole pressure. And that's only true at one depth. In a high angle hole, you can only have constant bottom hole pressure at one depth. As you continue to drill your lateral section, let's say you select your anchor point, that we like to call it, at the heel.
Mm.
You select your anchor point at the heel. As you drill the lateral section, it has to increase. Your annular pressure is increasing, but your TVD is not increasing. So the ECD has to go up. Well, if your margin is relatively narrow, or let's say you've got a significant amount of ECD, if you've got a really tight annular clearance, that might not actually help you. It's I think that utilizing MPD can be very helpful in a lot of situations, and frankly, in some situations, it is not cost effective to employ an engineering solution to some wells. For example, we've done some wells with some companies in the Haynesville, where in order to mitigate their ECD concerns, they would have to literally drill a larger production hole size, which means their intermediate casing has to get bigger, which means their surface casing has to get bigger. All of that gets bigger all the way up, and it just makes it not economic, where they have the window, the hydraulic window, to be able to use MPD. That allows them to drill the wells within whatever limitations that they have successfully without having to completely modify their existing well design. But that's not the case everywhere. In some cases, it could actually be a cheaper long-term solution to design the wells to mitigate for the ECD as opposed to just throwing MPD on it and hoping that it's going to work.
So go back to the anchor point that you just mentioned. So the anchor point, that's the point in the well that the MPD engineer uses to calculate an ECD equivalent to hold on the well, right?
Correct.
So they're going to use that point, and that point's going to apply to the rest of the well. So what happens when we drill a lateral and we're halfway out? Do we not care about the rest of the lateral? How does that affect it? If we're not supporting the entire well, we're only supporting at the shoe, then we leave ourselves open to what consequences?
Well, there's always the possibility of encountering lost circulation, or breathing. If you're keeping it at the heel, then as you drill further and further out, it may get your ECD has to get higher, and depending on how you've set your anchor point, because your anchor point is going to be what's that TVD, what's the ECD that you have, how much surface pressure do you need to apply. It really boils down to what is the MPD engineer's plan for maintaining the bottom hole pressure within whatever hydraulic limitations you have, collapse gradient, and your fracture gradient, or your pore pressure, whichever is your narrowest mud weight window, which in high angle wells is typically going to be your collapse gradient and your minimum horizontal stress. That's where you want to try to keep your hydraulic window. So let's move on to tension. So when we talk about tension, the first thing that we want to talk about is slide drilling. So in most ERD wells, not going to say all because I'm sure that there's some out there, but most ERD wells, they use rotary steerable tools. And the big reason for that is because slide drilling is just not possible in a lot of these wells. The only way to overcome the axial drag, if you have to slide, is going to be either rocking the pipe back and forth or potentially using agitators. But typically in ERD wells, the operator's typically running some pretty big pipe in order to overcome the standpipe pressure concerns. So if you're already maxed out on standpipe pressure, then adding agitators doesn't really benefit you. So that's why they typically use rotary steerable tools. But if we wanted to, if an operator wanted to consider it, then you would look at, like looking at this plot, we're looking at a tension snapshot plot where we've got measure depth on the y-axis and effective tension on the x-axis. So this is a snapshot plot showing the tension at every single point in the well, and we're looking at a depth of 15,500 feet. We're looking at sensitivity to weight on bit, so 5,000, 10,000, 15,000, 20,000, and 25,000 pounds. So this is 5, 10, 15, 20, 25,000 pounds. The green and the red curves over here on the left are our sinusoidal and helical buckling limits, respectively. So when these curves start to go into these green and red zones, then the pipe at that specific depth, based on that sensitivity, is going to be buckled to a certain extent. The key here for this plot is this 0 mark right here. This is the effective tension at surface. So the top joint of pipe at surface, as long as we still have tension in that pipe above 0, then we're still going to be effectively able to transfer weight down all the way down to the bit at that depth. As soon as we start to go below 0, then that means that at that point we would have to start applying weight with the top drive to apply that additional amount of compression. And these curves over here that have kind of snapped all the way off to the left, these curves are essentially indicating that we would have lockup. So the pipe has become so buckled, so helically buckled, that the pipe is essentially coiled itself into the side of the hole. And as we start to apply more weight downwards, it's just pushing harder and harder into the side of the hole. It's acting like a set of slips down hole. And that's why you just can't apply any more weight when you get into a locked up state.
So according to this plot, I would only be able to put about maybe 11 downhole. And to get 16, I would have to basically drop the top drive on it.
That's correct. So what we're looking at right now is we could apply 5,000 pounds weight on bit according to this curve, and it would be okay. We could apply about 11,000 pounds, maybe 10,000 pounds weight on bit, and that would be essentially going right down to block weight. Pretty much damn near right down to block weight. This plot indicates, or this line indicates at 15,000 pounds that we could apply 15,000 pounds of weight on bit, but that would require us applying close to 50,000 pounds of compression at surface. So that would be essentially sitting the entire weight of the blocks on top of that top joint of pipe, which is just not realistic. Mm. And in that case, it might not even be possible to not only drill the well, the cutters might not be able to engage in the rock, but even if they are, you're likely not going to have a stable bit face. And there have been so many stories about when people go to slide drill in many areas around the world, where everything's going real nice when you start to rotary drill. You go to do your first slide, and then of course you're not getting effective weight transfer to the bit. The bit then starts to get rattled around, it starts to whirl, it starts getting beaten up, and then after that first slide, then your rotary drilling goes to crap. You pull out of the hole and all the outside row cutters are all worn off, the bit's all beaten up, and a lot of the times it goes back to that first slide, because if you can't properly engage the rock with the cutters, then you can get into a vibrating state, which just is a very common cause of damaging bits and BHAs. And even in situations like this, it's very common where somebody might say, well, let's just throw some heavyweight on there. Well, in these types, in ERD wells, heavyweight just doesn't work that way. You don't have a whole lot of vertical section to put the heavyweight in to allow you to get that extra weight down. One thing that can be really interesting and needs to be well understood in high angle wells is what the friction factors are. The friction factors can be very sensitive to a number of different things. So whether you're encased hole, whether you're an open hole, and what type of fluids you have in the well that the drill pipe is interacting with, the drill pipe or casing interacting with. So this is an example from Alaska where we had run in, the well had been drilled, the casing had been landed, and we ran in with a displacement assembly because they wanted to displace from the existing fluid in the well to a brine. So as we ran in, so here's the measure depth in the x-axis, all the way down to 12,000 feet, and here's the surface hook load. So it's a driller's view hook load plot from 60,000 pounds all the way to 125,000 pounds. And we're looking at friction factors for slacking off. So all these curves are for slacking off, so we're running into the hole, from 0.5 to 0.25. 0.25 over here, so our lowest friction is over here, and our highest friction is over here on the left, and our lowest friction is over here on the right. As we run this string into the hole, we can see that we're seeing anywhere between a 0.10 and a 0.15 friction factor. After we displace the well to brine, and then we go to pick up the pipe, the exact same assembly, exact same well path, everything else being exactly the same, now we're seeing a 0.3 friction factor. So remember over here, we had a 0.1 to 0.15 friction factor. If we had that over here, then our pickup weight would have been 150 to 165,000 pounds, had the friction factor stayed exactly the same. But after displacing the well to brine, then we go to pick up, and now we're at 210,000 pounds. So we're seeing an additional 50, 60,000 pounds of drag.
Just for fluid change.
Just for fluid change. Brines historically, based on data that we've seen, are just a higher friction fluid compared to oil-based fluids. And in some cases, if we can see that this is perfectly following the model, that there's no indication at all that there's any issues with the pipe hanging up, or any solids in the well or anything like that. We're perfectly following this model all the way back. That this to me indicates the model is well calibrated, that there's absolutely nothing going on. But there might be some cause for concern when you initially go to pick up to say, wow, it really should have been 150 to 160,000 pounds, but it's actually well over 200.
So you need to have some sort of, I guess, history to understand this. I mean, if you go in and you displace, and this is the first well I ever did, I was expecting a 0.1, 0.15 friction factor, and suddenly we've got a 0.3, and are we dragging the equipment back up with us? We're thinking there's problems, but I think this project had some long-term historical friction factor values for displacing to brine, so they knew this was going to be the situation when it came out. So it was not a surprise when it came up, but it's a very interesting example of what happens when you change out the fluid, the way it affects your friction factor.
The other thing to also keep in mind, especially in areas, because this particular rig, it's a relatively stout rig, and they use the same pipe that they typically use for drilling. So here they're using 5-inch 1950 S135 drill pipe. But in situations where you could be running in with much smaller pipe to displace, if the engineer did the modeling to say, yeah, we saw a 0.1 to 0.15 friction factor, and they handed that off to the completions or workover guys who then were going to use some skinnier pipe, coil tubing, or something else like that, and they did some modeling assuming that friction factor after they displaced to brine, it might be a situation where they might not even be able to pull that string out of the hole, or if they do, they might be exceeding the yield limitations of the pipe just to be able to get out of the hole, just strictly due to increase in friction. And another topic that's an interesting one is whipstock. So in a lot of these ERD wells, it's not uncommon to go back in after a particular productive interval is produced enough oil and the flow rate is gone below that point where the operator says, okay, let's go and drill a sidetrack. Let's go and put a well over here where we don't think we've produced that much oil, and we'll leave this one be for now. So going to set a whipstock, orienting the whipstock is normally not a big deal, and running the whipstock is normally not a big deal. But for anybody that's run a whipstock, if you're in a low angle well, shearing the bolt that you have that's holding the BHA or the drill string to the whipstock is not that challenging. When you're in a high angle well like this, shearing that bolt can be a huge challenge because you just don't have that much weight to apply down. As we saw before, when we were trying to apply weight on bit just for drilling, we couldn't get much more than 10,000 pounds. Most whipstocks are going to require over 30,000 pounds of compression in order to shear that bolt. So if we look at this tripping tension snapshot, similar to that last tension snapshot that we looked at before, so measure depth on the y-axis, effective tension in the x-axis. Again, green and red are sinusoidal and helical buckling respectively, but here we want to apply up to 40,000 pounds weight on bit. So this is 0, this is 10, 20, 30, and 40. If we want to apply 10,000 pounds weight on bit, we need to go down to pretty much just above block weight. We're going to have a few thousand pounds hanging on the hook to apply 10,000 pounds down at the bolt. there's no way that we're going to be able to do that and actually shear the bolt with that amount of weight. This is commonly why a lot of operators, when they go to do set a whipstock, they might sit there for hours or days just kind of working it down,
Yeah.
just try to more or less break it due to fatigue instead of just trying to shear it. Looks like we have a question. The question is the loss of lubrication from oil-based mud? So yes, if we're talking about this particular example, they had oil-based mud in the well before displacing to brine. So in this particular example, we did have a relatively low level of friction, and that was from the oil-based mud. And then when we switched over to the brine, we saw a higher level of friction.
And this is I think this is metal to metal, so it's pretty.
This is all inside casing.
Yeah, it's pretty standard. There's no question about formation interaction.
Good question, though. So a couple of options if we wanted to try to get more weight down on this, to shear this bolt, would be to run some additional heavyweight drill pipe. Now, if we wanted to run some additional heavyweight drill pipe, that helps us out a little bit. But with the additional heavyweight, we could apply now about 20,000 pounds weight on bit, and we're still above zero. But once we try to go anywhere beyond that to 30,000 pounds, we would need to be applying close to 30,000 pounds of compression at surface. But that still only gets us to 30,000 pounds of compression down at the bolt, which we wanted at least 35. So this is still not really going to work. The other option would be to run a swivel. So anybody, the swivel master is probably the most common one, where it's essentially a clutch where you run it in your string above the point, at some point in the hole. And then when you activate it, then it actually will start to rotate everything from that point back up the well. So by having a swivel, that allows us to effectively transfer almost all the weight that we want down to the top of the whipstock. So by running a swivel, what that does is if we run that, say, one stand above the whipstock, then everything from the swivel all the way back up the surface is rotating. Now we're able to convert the axial drag that we were feeling that was preventing us from being able to apply that weight down into torque, so we can get much more effective weight transferred down to the bolt. The same premise that we use for a rotary steerable tool, that when we turn the pipe, now we're able to get much better weight transfer down to the bit.
And this is something we talked about earlier, is the swivel. I don't think a lot of people have ever thought about it or even seen it in operation. It's not a very common thing in U.S. land to use a swivel. So how does that work? So you orient your whipstock, right? So you set it whatever direction you want, and then you do ball drop to activate the swivel, and then it disengages the clutch.
First you'd orient your whipstock and then make sure that your whipstock is totally set. Make sure that the slips are completely set based on whatever the whipstock manufacturer's recommendations are. Some are pressure activated, some are hydraulic. Once you've confirmed that the whipstock is set, then the swivel master is a ball drop. So you drop a ball, that ball activates inside it, and then at that point it activates as a clutch, and then you can start to rotate. Now they do have some technical requirements on how many rotations you can put it under, based on how much tension you have across the tool itself. But for situations like this, where we're literally talking about running this in, there's very little tension being felt on this tool, very little compression being felt on this tool. After you get it set and you start to rotate, you're going to be doing this for a matter of minutes, hopefully, and then apply that weight down, shear the bolt, and then you come out of the hole with it.
Rather than spend all the time working it up and down with fatigue. I mean, it could be hours. I've seen these take hours and hours before. So it's a tremendous amount of time savings to utilize a swivel to transfer that weight to your shear bolt or even your liner hangers, whatever you need.
Well, and that kind of we'll get to that in just a minute. We also wanted to talk about casing running. So casing running, in a lot of these ERD wells, the most common high angle tangent section that you drill is a 12 1/4 inch section where typically a 9 5/8 casing is being run. In this particular well, it was 9 5/8 40-pound casing, and we ran it out to about just around 13,000 feet. Now, the weight of that casing is massive. When you fill that casing with mud, it weighs a huge amount. So not only does that add to the drag of trying to push that casing to bottom, but it also makes the torque really high if you want to rotate it. And even in this particular well, we were running wedge 563 connections, which are probably some of the highest torque rated connections available on the market. We would still be well in excess of that torque limit. So we could not just simply run mud-filled casing because the drag would be way too high. We couldn't physically slide the casing down to bottom, nor could we rotate it because the surface torque would be way too high. It would exceed that of the top drive and even if we had a giant top drive, the torque, the connections wouldn't be able to handle it. So for this particular operator, they decided to both run the casing empty and to rotate it. So by running the casing empty in 9.3 mud, so 40 pound per casing mud, because of the buoyant force. So now we're using buoyancy to our advantage. The buoyant force is the force that's exerted on an object, and it's equal to the weight of the fluid that's being removed. So because 9 5/8 removes a lot of fluid, it has a pretty high buoyant force. That effectively, that 9 5/8 40 pound casing in 9.3 mud effectively weighs 7 pounds per foot. So we reduced the weight of the casing by over 80%, which means we've also reduced the drag and the torque by over 80%. The one thing that then comes into effect that we normally don't think about when running casing, but becomes a big deal when the casing weighs almost nothing, is surge effect or hydraulic lift. So when we go to run this casing into the ground, in theory, if we weren't taking into account hydraulic lift, this casing should just slide right to bottom.
Yeah.
But as we go to run that pipe in the ground, because the surge pressure is not terribly high, but because there's a lot of cross-sectional area, it's actually pushing back up against that casing shoe, preventing it from going down.
Yeah, that's something that we run into a lot when we float casing, is just that right at that balance where you're negative and you're having to use top drive weight. And it looks like they use a little bit of top drive weight here to rotate this casing down.
They did.
So I usually leave it to the driller. I call it driller's intuition, and they figure out the right parameters. Usually it's around maybe 20 RPMs and 15 to 25 feet per minute. That kind of parameters to run this stuff in. But it's doable. It's definitely doable. It's a little uncomfortable. It's your first time to ever do it. It's a game changer. And one of the things I've noticed lately, a lot of U.S. land operators, like the Marcellus and the Permian, are doing a lot of floated casing, whether it's mud over air. I think a lot of them are just doing the mud over air in these longer laterals that they're drilling, which is different than it was several years ago when everybody was just running conventionally casing. So it's a very interesting topic, and how to run it and how to use the. There's a particular there's a method to it, and you have to learn it. You have to see it.
Yeah, like for this particular well, what they would do is they would pick up a new jointed pipe. They would make up that jointed pipe, and then they would engage the casing running tool. And as soon as they started rotating, then the casing would just start to slide into the hole at like 1,000 or 2,000 pounds below block weight. So they're just barely using the blocks to push this thing into the ground. On the U.S. land side, the one thing that really needs to be taken into account for people on the U.S. land side that are doing mud over air is that buoyancy assist collar that's typically being run. I think NCS is the company that uses or that manufactures that tool. It's almost like a ceramic dome that they use to separate the air and the mud. So you're running the air down below to keep that part of the casing light, then you're going to run the mud up top to give you the extra weight and push that down. If anybody's going to use that, please make sure you engage with the supplier early on, because those are set up for absolute pressure, not differential pressure. So if you're going to set it at a specific depth and you're going to be running with a specific mud weight, they will set that tool up to be tooled based on what you tell them. But if for some reason you decide to run it a bit deeper, or you have to maybe a well control event or a wellbore stability event, you have to run higher mud weight. I don't know that it's happened, but in theory it could happen where you could have it break prematurely just based on the fact that you're not, that you haven't, that what was done in the planning phase wasn't translated over to the execution phase.
And planning, it's another interesting part is placement of this in the string. You're balancing your weight transfer and your ability to rotate it as well. So placement's and we've gone back and forth with several operators on this. It's like, where do we want to put it? Do we want to start rotating early? Do we want to start rotating later? Do we want to get as much conventional running as we can before we switch over to this mud over air system? So that's just things to think about when you're doing the engineering for this.
And sometimes when you're doing it as well, depending on where you put it, you can actually go from running your casing conventionally to having to rotate it to going back to running conventionally. After you get that heavier pipe, heavier fluid in the vertical section. That might actually allow you to go back to running it in conventionally without having to go back to rotation. Because I know a big concern that many ops guys have is they don't want to spend as much time rotating because it just takes long. And it's totally their prerogative which direction they want to go, but you can't fight the laws of physics. So lastly, let's talk about packers. So anybody that runs a liner hanger, almost every liner hanger system out there nowadays has an integrated liner top packer, and the packer has to be set after the hanger is set. So in many cases, you can pin the packer to have almost whatever setting you want. But a lot of the times, you're typically running into the 30,000-40,000 pounds of compression range required to activate the packer. If we're looking at this setup again, so effective weight or measure depth on the y-axis and effective tension on the x-axis, and we're going from 0 to 40,000 pounds. Oh, we got a question. What is the best practice for the displacement of air out of casing prior to cementing? That's a phenomenal question. So the best practice that we would recommend would be to hook up your cement head to your to the top of the casing. Have one hose going into the bottom that'll be filled with mud. One hose coming from the top that goes to your gas buster or your degasser on the shakers, and then just start filling it up. And as you'll have to close in the cement head, get to enough pressure to rupture that seal. And typically, if it's designed appropriately, they kind of design it where you would get to between 1,000 and 2,000 psi surface applied pressure with the mud weight that you designed at the depth that you've planned to run it at to get to the absolute pressure in order to rupture that disc. So use your cement head, start pumping in through the bottom, allow the air to displace out the top, and then just keep doing that until you get to a point where the casing's pretty full. You don't want to just hook up to it and start applying pressure at surface and then just start circulating. I know, like in theory, the pressure of the air below that airlock is at atmospheric pressure. So the theory is, and I've heard this from a number of people, and I can't really argue with them, is that as soon as that air gets outside of the shoe, there's going to be so much pressure on it that it's going to shrink to be something very, very small. And then you have to circulate it out like a kick. I've only heard from one customer that's done it that way, and they said, and the quote from the drilling superintendent was that the hole got real violent. So he said that he would never do it again. And the recommended practice that I would have be hook up your cement head to your top jointed casing, start filling up through the bottom line, have the top line go to your gas buster, and just keep doing that, because as you start to fill it up, it's going to start to burp, and if you just try to do it without that being contained within the cement head, it's going to make the rig floor really, really messy. So, getting back to the liner hanger, the packer situation. So again, this is another situation where the swivel would be an ideal tool for overcoming this challenge. So if we were to run this swivel directly above the liner hanger running tool, then that would allow everything above the liner hanger running tool to be rotating. So after we've set the slips, we've ensured that the packer is good to go. Then we go and engage the swivel. We start to rotate. We overcome that axial drag converted into torque, and then we can apply whatever weight we want to down to the top of the packer without any issues at all. And again, before just picking up a swivel and running it in the hole, if this is a challenge that you've encountered, please engage with the suppliers of that to make sure that the tools meet your specifications, because they do have some different specifications on how much tension they can be under. But by all means, it's a very powerful solution for applying weight down in high angle wells in situations that are a little more unique.
Yeah, this was an operation one time I watched for about 4 hours to watch this liner hanger hand set his hanger, and he could not get it done. The next well we did, we had a 15-minute meeting, discussed exactly what we were going to do, came up with a plan, had it set in 15 minutes. So it's planning ahead will save you a lot of time. Don't just assume that it's going to be the liner hanger hand has a plan in place, because he did not.
Well,
So,
and another thing that's very common for, and I this is not meant at all to be degrading to liner hanger hands, because I'm sure they've gotten a lot better over the years, but what I've seen before on a couple of projects I've been on, when we go to run liner hangers, is they want to take 3 pickup weights. They want to take one before you go to pick up the hanger. They want to take one before you get into open hole, and they typically want to take one right before you go to set it. And that's a pretty old school mentality, because if you're in a vertical hole, then yeah, you know, if you're in a completely vertical hole and you've got your casing in the ground and you pick it up, you know the pickup weight of it at that point. Before you go to set it, and you take your pickup weight, then you can take the difference off to say, okay, that's how much weight down I'm going to see when I disengage my liner hanger. But in a high angle hole, that's not really effective. It's really important to understand that if you need to apply a certain amount of weight down, like what we were seeing before, if you were just going purely off of compression, you would have to apply an absolute ton of weight at surface in order to get any sort of weight down at the BHA. So it's not an easy calculation that has to be done. This is something that can be easily modeled, and I have seen many liner hanger hands that do this on the regular. But going back to what we talked about before with swab, the worst swab you will ever get is with casing, because you've got the smallest annular clearance. And I've seen numerous projects where wells have been completely destroyed because they took care of the well while drilling, they did everything right, and they get close to the TD and they decide to take a pickup weight with their casing, and the hole is completely destroyed. I heard a story from a guy they used to work with that where he said he was on a rig in the Gulf of Mexico and he was taking pickup weights with casing, and the driller was some guy from Mississippi, and he started to give him all kinds of hell, saying, "Why are we picking up this casing?" He's like, "Well, we need to understand what my friction factors are." And this old driller was like, "Casing's only got one direction to go, and that's down." And he's absolutely right. You should never pick up your casing. If the liner hanger hand ever wants to take a pickup weight of casing, I would really question what he needs that for, and ask, why can't we model this? There's got to be a way for us to calculate what's required to set your hangers, set your packers, without having to potentially damage the hole by picking up the pipe.
Agreed. I've run across that several times. And we actually took the pickup weights. I lost that argument. We took the weights, and I was I think 1,000 off the modeled weight. So the models are pretty accurate.
They definitely can be in the hands of the right people.
Yeah.
Okay, we've got a few more questions. Okay. So unfortunately, that's all the time that we have. We will address these questions online at a later time. So we'll definitely follow up with anybody that has asked any questions. Please don't hesitate to ask any more if you have any more questions, and if there's anything else that you'd like to know, we're always here to answer them. Thank you very much for everybody who attended. And I'd like to recap that if anybody has an interesting topic or would like to potentially be a guest speaker on pre-tower with K&M, by all means, please reach out to us. David Gibson's Gibson Reports and Vidor Locksmith is going to be on right now. I think it started a couple minutes ago. So please go ahead, hit the like button, tell all your friends, show up next month, and thanks again for tuning in.
Thanks, guys.